where is the particle in average? So now that we have the wave functions n, labeled by the quantum number n, we can compute the average position in these eigenstates. So to do that, we do the usual trick. We insert the identity here. So this gives us dx n x x, and this is the operator n, and we have dx, the integral from 0 to a, and x is psi n star x, and then we have bra x applied to the operator x, so it's just x, and then we have x n, which will give us psi nx, and this is the integral from 0 to a dx of x psi n x squared. But we know psi n, it's simply so x and 2 over a sine squared n pi over a x. And this we can use an identity for the cosine, which is 1 minus cos 2 n pi over ax over 2. This will be simpler to integrate. So now we have this integral, and the first term is simply the integral of, so let's put, oh, and we forgot the 2 over a in front. So let's simplify the 2 here with the 2 here. We have 1 over a integral 0a dx of x minus x cos 2 n pi over ax. The integral here is simple to compute. It's simply x squared over 2 from 0 to a. And then we have this integral from 0 to a of x cos 2 n pi over ax. So the first one gives a squared over 2. And for the second one, there are two possibilities. Either we shift with a change of variable in order to integrate from over a symmetric interval, and then we will have the integral of an odd function over a symmetric interval, which will be 0. Or we can do integration by part so if you remember, integration by part, it's the integral of u prime v is equal to uv minus the integral of uv prime. So here the good u prime to choose is the cosine. and the v is x. So this gives us a u that is a over 2 n pi sine 2 n pi over ax and v prime, which is 1. So we have this following integral by part, which will be uv, so a over 2 n pi sine of 2 n pi over ax from 0 to a, minus, so there is already a minus, so plus uv prime, so a over 2 n pi sine 2 n pi over ax v prime, which is 1, from 0 to a. So we have 1 over a of a squared over 2. Now we have sine 2n pi over a times a. So here the a will cancel out for the first term here. And we will have sine of 2n pi. But sine of 2n pi is 0. So this one will give 0. And minus sine of 0. So the whole thing is 0. Now we have the other term, which is a over 2n pi, the integral from 0 to a of sine 2n pi over ax dx. But this is simply a over 2n pi of a over 2n pi of what? Of minus cos 2n pi over ax from 0 to a. And we have a squared over 2n pi squared, and we can put the minus here. So we have cos 2n pi over ax from 0 to a. So for a we have, so if you remember the trigonometric circle, 2 pi is here. So each time we do 2 pi, we will be here. So 1 minus for 0 cos 0, which is here. So 1. So this is also 0. So in the end, we have 1 over a of a squared over 2, which is simply a over 2. So this is quite remarkable because it means that for our wave functions in the infinite square well, so we have the first one, the second one, etc., etc. No matter what the excitation of the particle is in this box, no matter the energy it has, no matter which energy level it is in, if we measure, so if we look in the box, so if we look inside this box, in average, we will find the particle to be in the middle at a over 2. And this is a result that is valid for all n. So all the eigenfunctions of the quantum particle in average are centered at a over 2. But now we ask in average, what is the spread of these wave function psi n, of these eigenfunctions? To do that, to answer this question, we will compute this time the average of x squared. So this is, again, we insert the identity here, and we have 0a dx psi n star x, this time x squared psi n x. And again, we have the integral from 0 to a of dx 2 over a x squared 1 minus, well, we can do the step before, like before, sine squared n pi over x equals 2 over a 0a dx x squared 1 minus cos 2 n pi over ax over 2. So now we have this x squared that is here, and simply we will apply our integration by part iteratively, so 2 times, in order to reduce the order of this square. So we have 2 over a of 0a dx x squared over 2 minus, oh, this over 2 here we can actually simplify with the 2 here. And we have the integral of x squared minus x squared cos 2 n pi over ax. So we have 1 over a of x cubed over 3, which is the integral of x squared from 0 to a, minus the integral of 0 to a x squared cos 2 n pi over ax. Now, so the first part is a cubed over 3, and for our integration by parts, we take u prime equals cos 2 n pi over ax, v equals x squared, u will be a over 2 n pi sine 2 n pi over ax, and v prime is 2x. So we have uv, which is a over 2 n pi sine 2 n pi over ax times v, so x squared, from 0 to a. And I will write it here. So this minus 0 a dx a over 2 n pi sine 2 n pi over ax v prime, so 2x. And we have 1 parenthesis and 2 parentheses. This gives us a squared over 3 minus, so again here sine 2 n pi over a times a is sine 2 n pi, which is 0, and sine 0, which is 0. So this is 0. Then we have a minus here, a minus there, so it's a plus. plus we put the constants out, so we have a over n pi of 0 a dx x sine 2n pi over a x. And this we can simply reuse one of our and here we simply redo the integral by part, and it gives us so a squared plus a over n pi times, so let's take u prime is equal sine 2n pi over ax, v equals x, v prime equals 1, and u prime, so u, sorry, equals a over 2n pi cos, so minus a over 2n pi cos 2n pi over ax. So we have a n pi times uv, so minus a over 2n pi cos 2n pi ax times v, which is x from 0 to a. And we have minus uv prime, which is plus, because there is this minus sign here. So plus u a over 2n pi cos 2n pi over ax v prime, which is 1. A squared over 3, and there is a 1 over a missing from there. There should have been 1 over a here and here as well. So we have a squared over 3 plus 1 over n pi of the integral here, which gives minus a over 2n pi cos of 2n pi over a times a, which is 1 times a, so a, minus cos of 0, which is also 1, but the whole thing by times 0, so 0, plus the integral of this cosine here, which will give a squared over 2n pi squared sine 2n pi over a x from 0 to a. And this gives 0. So in the end, what we are left with is that the average of x squared is a squared over 3 minus a squared over 2n squared pi squared. So even though the average position does not depend on n when we are computing the average for the eigenfunction n, the spread does actually depend on n. And the larger n gets, so when n goes to infinity, we have x squared, and that will go to a squared over 3. So the larger n gets, the larger the spread, and we can see this in the first few wave function plots above. The first, for n equals 1, we have this. So the spread is small in some sense. But when n is large, we will have something that is very oscillatory, and the probability to find the particle across the whole interval from 0 to a will be more spread out. But still the average will be in the middle. Okay, now that we have seen these things, we can look at one last interesting question, which is what happens if we have a superposition and let it evolve in time? What will happen to the average position x?